Yeah, so good afternoon to all. My name is Alexandru Ghiurca, and I'm a project advisor working at CINEA, so the Climate Infrastructure and Environment Executive Agency of the EU. And welcome to this afternoon session dedicated on solid-state batteries for electromobility. We have quite a big panel today, so we will start already now, and if there are others joining us, they are, of course, welcome to join us. So as a very short introduction, you all know that the electric vehicles market is steadily expanding across the globe, as this is seen as part of the solution to fighting climate change on one side and achieving sustainable mobility. But on the other side, you all know that Europe is lacking behind in terms of manufacturing high-quality electric batteries, and in particular solid-state lithium-ion batteries, which deliver in terms of performance, but also safety, sustainability, increase the life cycle, and so forth. So in this context, for us at the European Union, it's imperative basically to improve the development processes of these materials in order to reach the ambitious targets that Europe has set in terms of climate ambitions and mobility. So there are a number of projects that we financed over the years, some of them under Horizon 2020 and some under Horizon Europe. There are two topics in particular that address this issue of solid-state batteries, one of them being the strongly improved, highly performant and safe all-solid-state batteries for electric vehicles, under which the project SUBLIME was founded. And it basically responds to this, let's say, needs of the EU for improving the cell design, but also to provide solutions for the optimal function of electrolyte materials, also to demonstrate suitability for high voltage electrode materials, and also to contribute to interface optimization, characterization, and integration, including multi-scale modeling. And then there is another topic that was founded under Horizon Europe, under which the projects SEATBELT, HELENA, ADVAGEN, and PSIONIC were founded, which aims to advance high-performance generation 4A and 4B, so all solid-state lithium-ion batteries, supporting electromobility and other applications. And the aim being, again, so to improve the design and the performance of the lithium-ion batteries, delivering on cost, performance, safety, thermal stability, suitability, but also to demonstrate their potential for micromobility sector, and also to provide high-power variants for the fast-charging, airborne, heavy-duty, and hybrid segments. So today we have quite a number of projects that we'll be presenting in the coming minutes. And I will give the floor to each of the speakers one by one. So please, you would have 15 minutes for your presentations, and afterwards in terms of questions, so if you have any pressing questions for clarifications, you can ask them just after the presentations, while we have a more dedicated questions and answer session at the end, where my colleague Guinevere Giffin from Fraunhofer Institute for Silicate Research in Germany will lead as well. So without further ado, I will give the floor to the first speaker. So for Project SUBLIME, it will be Mr. Sayed Hossein Payandem, who is Battery Technology Specialist at FIV Europe, will present you the project. So please.
Hello everybody, good afternoon. It's my great pleasure that today I can present the result of SUBLIME. This project, I go to the next slide. Yes, this project started in 2020 and finished just last year, December 2024. And as you can see here, sorry, this one is for the pointer. Okay, no worries. Yes, so as you can see in this graph, there were 15 partners involved. So there were parties for making materials, parties for fabricating cells, and also automotive industry were also involved at the end to evaluate the cell performance. So the aim of this project was to make all solid-state battery. It was a very challenging project to start with high nickel cathode materials, nickel content of above 80% to be compatible with the state-of-the-art lithium-ion battery technology. So with the lithium metal anode to boost the energy density of the cells, and with a sulfide solid electrolyte. And the projected energy density of the cell was above 450 watt-hour per kilogram. And the aim was to make multi-layer pouch cells up to 10 ampere-hour in size. So some of the objectives of these projects I have listed here. Some of them we go through this in the next slides, and some of them I will already answer here. So as I mentioned in the beginning, we have the high energy density for above 400 and the one above 400 watt-hour per kilogram and above 1,000 watt-hour per liter. Cyclability, so the cells should have a very good cycling stability of more than 500 cycles. Then, of course, the low cost. So in this project, we calculated that the cost of the cells could be down to 75 euros per kilowatt hour if the cost of the solid electrolyte is below 50 euros per kilogram. Then the material and the cell should reach a TRL level of 6. And of course, the cells should show high safety, high thermal stability, and they should be sustainable. So in this project, we have defined a recycling route with efficiency of more than 90%. So we can recycle all the solid electrolyte back after the end of the life of the cell. And here in this project, I can quickly show you how the cell development took place. So in the beginning, we start with materials. We have to develop the materials for our cell chemistry. For example, we have to develop a desired solid electrolyte, desired cathode with a special coating, and lithium metal anode with a special coating as well. And then we test these materials in a coin cell format. In the next step, so because we want to make a large multi-layer pouch cell, we have to make electrodes. And then with the developed solid electrolyte, with the developed cathode materials, we have to make electrodes. And then we again test this first in a coin cell, then in a single layer pouch cell, and last in a multi-layer pouch cell. So this is the development path that we followed in the last 4 years, from material towards electrodes and at the end towards making the final cell. So for materials development, so a special cathode has been developed in this project. This is a single crystalline NMC with high nickel content and with a special coating that we can use for a sulfide solid electrolyte. And Umicore has developed such cathodes. And we received more than 3 kilograms of this product during this project. Solid electrolyte was also developed in this project and in kilogram scale with high ionic conductivity. So we followed 2 passes, one for normal cells, and the ionic conductivity was 2.5 millisiemens per centimeter. And for high power cell, we developed another generation of solid electrolyte with more than double ionic conductivity. And Ciensco was the main partner for developing this electrolyte, and they produced it in kilogram scale. So for the anode, because we are using a lithium metal anode, it is very challenging. Our partners, ABEE and TNO, were responsible for making stable coatings to apply coatings on lithium metal anode and make it stable. And we deposited a special aluminum oxide on a lithium metal anode, and we went through several iteration steps to optimize this coating, and at the end, our partners could deliver 1.8 square meter of this coating. So this is on a material level. And this is just an example of how, by tuning our materials, we can improve the performance of the cell. For example, on a coin cell level, this is the performance we had at the very first of the project in the first year. So we could only get 30 to 40 milliampere hour per gram capacity. Then we optimized the material, the capacity improved, and at the end of the project, at the end of the year, and at the last year, at the coin cell level, we could reach 190 milliampere hour per gram at silver 20. And at 1C, we could get 120 milliampere hour per gram. So, but the main challenge that we have identified is that the lithium metal anode was considered as the main challenge because the coating, it was very difficult to source lithium metal anode with high quality, and also the coating of this was very challenging. So as an intermediate solution, we proceed to make cells with indium anode. That this allows us to fabricate electrodes, cathode electrodes, solid electrolyte layer, and fabricate the first cells with the indium anode. And later, when we have the lithium metal anode, so we can fabricate the final cells with the lithium metal anode then. So this. So we took this solution of, we said, okay, we need more time to focus on lithium metal anode. Meanwhile, we continued with solid electrolyte and cathode. And as you can see, for example, in the picture, AIT has developed a solid electrolyte film in this project. It's a freestanding solid electrolyte layer. They tried many different binders, many different solvents to come to this final product. Then cathode electrodes were fabricated by Fraunhofer IST. They also optimized the process to be able to upscale these electrodes. And here you can see the initial cells with lithium metal anode, with indium anodes. We made these cells. And the first generation of these cells had the energy density of 100 watt-hour per kilogram and 225 watt-hour per liter. So it was below our target, of course. However, in these cells, we were focusing on performance rather just to maximize the energy density, because this was the first generation of the cells and we wanted them to really work. And so the solution to increase the energy density is that in the first generation, the thickness of the solid electrolyte is very high. It is around 250 micron. So we have to reduce the thickness to at least 15 micron, and we have to increase the cathode loading. So here is, I have shown in this animation at the bottom. So for us, it was the cathode loading low and the solid electrolyte thickness very high, that resulted in this low energy density. However, in the next generations, we can step by step tune this and reach the final energy density that's required this project. Then we tested the cell. So we made so if you want to slide back. So we made 18 cells with indium anode, 18 cells with lithium anode, and then we tested the cells. So for testing, this is the cells with indium anode and lithium anode. You can see both of them. The cycling performance is stable. However, we can see that the capacity is much reduced, and this is because the process of the electrode was not needs further optimization, I can say. So at the moment we have a stable cycling, so we can reach 250 cycles. The cell is working. However, in the first step, for the formation, we lose capacity still. And this is mainly for the cathodes that we have produced and the lithium metal anode that they still are decomposing a little bit in the first steps of charge and discharge. Then in the next step, we wanted to measure the thermal stability of the cells, and we did abuse testing. So we made a 1 ampere hour cell we needed a large cell that we could rely on the testing result. So then we heated up this cell, and we saw at around 120 degrees, the voltage is lost. At around 280 degrees, some gases started to release, and at 400 degrees, so we heated up to 400 degrees, and you can see the pictures on the right side. So the cell was safe. So at around 280, some gas released, but no real thermal runaway took place in these cells. Then last step was also simulation. So we did P4D modeling at coin cell level to see what is the degradation, what is the main reason for degradation of these cells. And the main outcome of this modeling was that in the first step, we have some reduced capacity, and because of the decomposition at electrodes. However, after cycling, this capacity fade is mainly attributed to contact loss of materials, for example, contact loss of the cathode particles with solid electrolyte or binder, or in general, the loss of this active material. So in this project, this was the first type of the project, of EU project for solid-state batteries. So we had a lot of learnings, how to make these all solid-state batteries, how to make electrodes. We upscaled cathode materials, solid electrolyte, lithium metal anode, and so on. And now our company is now involved in 4 more EU projects: ADVAGEN, HELENA, Nexel, and Halide. So my colleagues would present them. And for example, with ADVAGEN, a colleague of me is presenting this project tomorrow. And in this project, they use oxide and sulfide hybrid electrolyte as a solution to overcome the challenges of instability of sulfide electrolyte with lithium metal anode. So this is a continuation of what we achieved here towards making better performance. And so in this project, the impact, quickly go through the impacts. So a lot of students were trained, a lot of knowledge was obtained by processing these materials. So we developed materials at kilogram scale: solid electrolyte, cathode, lithium metal anode. This electrode we fabricated, and life cycle analysis. We developed a recycling path with 90% efficiency, and simulation techniques. For example, the final results were presented to the European Materials Modeling Council. And at the end, we published 14 open access publications and presented the results in 23 conferences. Yes, thank you very much for your attendance. Thank you.
Thank you very much, Arash. Is there any question for Arash for clarification? Sorry. Yeah, I don't know why. Sorry, it moved at the beginning of the presentation. Oops. Well, here you are. Okay. If not, thank you very much, Arash.
Thank you.
And next speaker, actually there are 2 speakers for Project HELENA. It's Mr. Pedro Lopez, who is senior researcher at SICA Energegun in Spain, and Sara Abada, who is senior researcher at IPF Énergie Nouvelle in France. So please, the floor is yours.
Okay. Hello, everyone. So first of all, I would like to introduce myself. My name is Pedro. I am a senior researcher at CSE Energigune, where we are coordinating this HELENA project. And I'm very happy to also introduce to Sara. She comes from IFP, Énergie Nouvelle, and she will also be presenting the project. I would like to thank her for coming here. So to make it more refreshing, I will be presenting the first part of the project, introducing the goals and the approach that we are following, and then I will leave the word to Sara. She will be more focused on the multi-physics, multi-scale battery modeling approach. So to briefly introduce HELENA project, we started in 2022, and you can see here a picture of the kickoff meeting with all the partners involved in the project. And actually to follow on the previous project that was presented on SUBLIME, we have a similar goal as SUBLIME, but we have a completely different chemistry. But as Aras was saying, there was a very good learning from the SUBLIME project that has allowed to most of the partners, which are also part in HELENA, to start from a higher point. No? So here you can see the contribution on the whole battery value chain from HELENA project. We are covering all the aspects of the battery chain, since we focus on increasing the TRL from 3.4 to 5.6 at the end of the project. And so we have in the project materials manufacturer with key or core materials on the proposal, mainly the solid electrolyte halide material, which is provided by Saint-Gobain ceramic industrial manufacturer. But there are also core materials like layer oxide active, high voltage active materials provided by Umicore, and also partners involved in the development of a lithium metal anode. There are also other partners involved in the battery component processing, so to develop the electrolytes, the self-standing films, and all the components that are needed for the battery. And we also have partners in charge of testing the batteries, validating them on the specifications that are set. And there is a partner which will be in charge of upscaling the technology, let's say going from the lab scale to a large pouch cell manufacturer of 10 ampere hours. And finally, we have also the partners involved in the battery modeling, which is a transversal task during the whole duration of the project. Here, I would also like to point out that these batteries are intended to be applied in electric vehicles and also for aerospace applications. So we also have the presence of partners setting the specifications for aeronautics and for electric vehicles. This is a summary of the goals of the projects that we have and the specific KPIs. It can be summarized in the following ones. So on one side, we have specifications of the battery that are, as I was saying, that are defined by the end users on electric vehicle and aerospace applications. So here we're targeting high energy and high energy density batteries with a long cycle life, also increasing the stability under high temperatures, and keeping also as well the safety as a key requirement for these applications. In terms of materials, we have KPIs defined for the solid electrolyte. Here we are working with a halide material which exhibits a high ionic conductivity, but there is also a whole work on the project on how to improve the electrochemical properties of this material as core of the battery. Cell configuration, so it has also to be stable against the active material, and towards the lithium metal anode. There is also development and engineering of the active material. Here we are dealing with high voltage NMC. And so there is activity around these active materials with development of coatings to ensure higher rate capabilities. And there is also activity on lithium metal. Lithium metal is a key component for all the projects that are going to be presented here. And it's actually very important to develop solutions for lithium metal, because as we are pushing forward the energy density of the batteries, so does the reactivity of the materials. So halides are very reactive, can be very reactive towards lithium metal. This is why we need to develop coating solutions to prevent degradation and to ensure performance in the long term. And so finally, the goal is to make these prototypes of 10 ampere hours to demonstrate how this chemistry positions on a scenario in which there is still a lot of uncertainty on which solid electrolyte will be the most appropriate. And you can also see the solid state cell configuration, where we have these layer schematics of the battery. As an approach for this project, we have 3 main phases. First phase deals with all the materials sourcing, so the fabrication of the solid electrolyte, the development of the cathode, and the lithium metal protective with the protective coating solutions. In parallel, there is also an optimization task to really optimize the electronic properties of the halide material, pushing forward the ionic conductivity, the coatings of the active material, and the anode interfaces. On the second phase and core of the project, and it's where we stand now, we are processing all those materials, raw materials, into battery components. That means the extrusion of the components to prepare the cathode laminates and the self-standing electrolytes. We are aiming for very thin layers of halide electrolyte to reach the energy density that we are targeting. And finally, on the later phase, we are making these prototypes from a lab scale, from a lab cell scale to large pouch cell for final validation in the application with the specifications that are set by the end user. So in this whole phase, there is the transversal activity of the battery modeling, which serves as a guideline to help to make better materials and to build better solid-state batteries. And to go on with our overview of the results that we have achieved so far in the 2/3 of the project that we are now. So first of all, there was the establishment of the electric vehicle and aircraft requirements. So here we have all the inputs that are summarized in a detailed report from our end users from the aeronautic and automotive sector. So basically, I won't go into details, but just to mention that both applications share some of the battery requirements. However, for the aeronautic application, there is a high weight sensitivity of the battery. So, and as well, this application requires for a higher power output. Of course, for both applications, safety and reliability are very critical. On the experimental side, there's been a lot of materials optimization. If we take the solid electrolyte as a core material here, our industrial partner has been able to manufacture several generations of this halide electrolyte at a large scale. And with that, they managed to obtain high conductivity material with 5 millisiemens per centimeter, which will ensure, hopefully, the performance at higher rates. And also, as an important property of the material, they managed to decrease and to homogenize the particle size to ensure a good contact between all the materials within the battery. On the side of the active materials, same. There's been also good progress on the two families of NMC that were developed with lower and higher nickel content. So here, what I can say is that we now have NMC with rich in nickel, which has been optimized in terms of particle size and surface coating that will ensure the performance of the cells. We took those materials to process them into components, and for the moment, we had already cells that are being done at lab scale. You will have details on the electrochemical performance on publications that are coming out of this project that will be listed later. And here what I can say is that now we are on the stage of fabricating these self-standing membranes. So we now have thin self-standing membranes of 100 microns, but we are able to decrease down further. So hopefully we will reach the target of the project of 30 micron. In parallel, there is also being a lot of work on making the composite cathodes with NMC and the halide. And we are now on the step of making the multi-layer pouch cells. So there are partners involved in processing with extrusion are now investigating how these materials can be processed. So now I will leave the word to my colleague, Sarah. I'm very sorry because I took a lot of time.
Thank you, Pedro. Hi, everyone. I'm Sarah from IP and Guinevere. I'm happy to be there today. And I will continue with the results from HELENA project. And we're talking about the modeling works. In the HELENA project, we developed a modeling framework based on multi-physics and multi-scale modeling adapted for Gen 4B batteries. In this framework, we identified 4 different scales from material to the pack level. So we are using atomistic modeling to identify the properties of the materials for both electrolyte and cathodes. At the electrode scale, we are dealing with microstructure modeling, and the objective here is to model the calendering and the stacking process. At the cell entire level, we are developing a macro-scale continuum modeling to assess the behavior of the cell and to assess the performance, aging, and safety. At the pack level, we have a simulation system to simulate end-user profile for both aeronautic and automotive application. I hope that you trust me if I say that today we don't have one interface or one software to assess all these skills. So the deal is how to connect all these modeling skills, how to identify the input and output of all these models. And in the HELENA project, we defined a network in which we identified these input and output. And now we are using this approach to assess the design and the assembly of the cell. At the atomistic modeling, we tested and studied different generations of the solid electrolyte. At the microstructure modeling, we are using a discrete element model to model the stacking and the calendering from an initial arrangement of the SI particles. At the microstructure model, we are using a single particle model, and here we have an example to assess the impact of the external pressure on the performance of the cell. And the idea in the next month is to use and reduce this model, these physics-based models, for the system simulation and be able to simulate user case from both aeronautic and automotive. We are dealing with the recycling as for the different projects today, and we aim to have 75 recycling efficiency and 18% of lithium recovery from the Halide. And today we are sure that recycling is more complex and challenging with generation 4 comparing to commercial lithium. Yeah, today we have 2 patents related to the preparation and treatment process of the Halide electrolyte. We disseminate with 2 published articles, 3 submitted, and hopefully in the upcoming months more than. And for the impact of the HELENA project, for sure in the technical aspect, we are innovating Halide electrolyte with optimized component for Gen 4B battery. Our approach for modeling is interesting and can be used for further development and other projects. For example, here our developed models are, the approach are available in the public deliverable. Yeah, for long-term impact, we believe that we are pushing and encouraging investment in next generation 4B. We are supporting Europe with all these optimized materials, and we hope for the future research taking into account all the gaps and challenges that are identified within the project. We would like to conclude here with some idea and some suggestion based on our experience in HELENA project and other projects. For the action in the future research, it will be interesting for the materials to take into account and to consider hybrid electrolyte. That can be very interesting. For thermal runaway, yeah, we can easily say that Gen 4B is safer than conventional cells, but it will be very interesting to go further and to improve the management system for this next generation battery. We need also to consider fast charging and to adapt materials architecture for that. And of course, we push to use digital twins and automation in both cell design and battery assembly. Yeah, it's all. Thank you. Sorry.
Thank you very much to both Sarah and Pedro. Is there any question for clarification from the audience? Yeah, I see there is one in the back.
Thank you. Bozor Khanbay from BEPA, Batteries European Partnership Association. A quick question about the end users. So what has been the feedback that you got from the aviation stakeholders in terms of the KPIs that you have? Are there enough for them? I'm thinking, what's their perception of the metrics and the figures, and also anything that is we haven't thought of as a battery community about what they need, either in terms of a performance or integration, etc. In general, also, what's your take about the electric aviation in this kind of format that we are moving forward? Thank you. Yes. Thanks again for the presentation. Very nice one.
Thank you. So for the moment, the aeronautic end users, they are still at an early stage on the integration of these batteries into their airplanes. For the moment, it's just on small segments that they can that they are thinking to insert this technology, and for sure, solid-state batteries will offer for them an improved energy density and safety compared to the conventional lithium-ion batteries. So that is for sure a winning for them. Of course, they need to push forward on power, which is also very important. This is why in the proposal in this project, we are focusing on having a pathway that ensures this high power application. Of course, it is beyond what they would need, but it's still representative to have a demonstrator that can be used in this type of applications. So a starting point, I would say that it's enough for them.
Thank you very much once again. Then for the next project, which is PSIONIC, I would invite Mrs. Margot Lecuyer, who is Manager of Innovation Team at Blue Solutions. So please, Mrs. Lecuyer, the floor is yours.
Okay, thank you everyone. I'm happy to be here to present our PSIONIC project, which aims at developing a new Gen 4B battery generation. So in PSIONIC, we are a big consortium which covers all the value chain for being able to deliver this new generation of batteries. We coordinate the project together with Clearance, who is helping us on all the, let's say, paperwork, and on the technical side, we take the lead. There are other partners which are taking care of all the parts of the batteries. For example, for current collector developments, we work with Armor. For developing new polymers, we work with specific polymers, Politecnico di Torino, and NIC. We have the help of different groups that are able to make modeling in Uppsala, in Italy also. And for the lithium side, we work strongly with the MIT laboratory in Germany. Concerning all the recycling developments, Blue Solutions, together with Accurec, we are working on recycling all the different parts of the cell. And for the prototyping, we work also with CNRS, the lab in Amiens, to make the extrusion, to develop the extrusion for cathodes especially. And the end user is Renault Group, which aims at integrating our future batteries in EVs. So the project started in July 2022 and should end in July 2026. And the budget is close to 8 million euros. So what are our objectives? In the opposite of the previous projects you've seen this afternoon, we aim at developing a polymer battery. We will also use lithium metal anode, which will be very thin. And we will also use nickel-rich NMC on the cathode side. And in between, we are trying to develop a polymer which will integrate both the catholyte and the electrolyte. The aim at the end will be to reach very high energy densities, higher than 420 watt-hour per kilogram, and more than 1,200 watt-hour per liter. Of course, we want to reach also very high cycling lives in order to tackle different applications, not only EVs, but also commercial vehicles, etc. So our target is around 3,000 cycles. And of course, for EVs, you all know that we will need fast charging, so we need to improve all the performances and the power capabilities of our cells to reach 3 to 5 C performance at elevated temperature. I mean, with that we will not do fast charging at minus 20 degrees, of course, but at least between 25 and 40 degrees, we want to be able to fast charge. Maybe quickly, what we will develop in the project will be done in two times. If I come back to this slide, maybe it will be easier. So we will progressively move to these high KPIs. So progressively we will improve all the different components. First, working on, let's say, not optimized lithium, not optimized cathode, and not optimized electrolyte, and progressively re-inject the improvements to thinner the lithium, to thinner the electrolyte, to have a better conductivity, and to increase the energy density of the positive electrode. So let's go to results. So what we have done is to work first on the lithium anode. So our strategy is to lie on coatings to protect the lithium anode from the electrolyte and to increase its chargeability. So we have different approach, and we are comparing the different approach to select the one that will be upscaled. So these approaches are basically inorganic ones and organic ones. So as you can see, we have got very good results with coated lithiums. That gave us the ability to reduce both the polarization of the lithium, but also to increase the cycle life just with symmetrical cells. With inorganic coatings, we got these very good results, and we've also got very good results with organic coatings on below. As you can see, the non-coated lithiums were dying, let's say, very soon. But when we coat, we managed to have very good cycle abilities on the negative side. So these results were got with the PO tetraglime electrolyte, which was our, let's say, reference at the beginning of the project. On the electrolyte, so as I was saying, we started with the PEO-based electrolyte, but it's not our main goal. So we are trying to improve this electrolyte to make it functional with the NMC electrode and at lower temperature. You all know that PEO cannot work at room temperature, so we are trying to reduce or to increase, let's say, its conductivity at room temperature. And PEO is not stable against NMC, so we need also to make changes in terms of chemistry to make it happen. So on the left, you can see the first results with the basic electrolyte. It was not working at all when we put the NMC cathode in front of this PEO electrolyte. So we had to change the chemistry inside to make it functional. What was interesting in this project was that we discovered that even with cyclic voltammetric measurement that were good at high potential, still 4.5 volt, when you put the right electrode, it's a completely different world. So our electrolyte was, let's say, stable in theory at 4.5 volt. But when we put it against NMC, it was not functional. So we are currently redeveloping the electrolyte, improving it to make it compatible with NMC and allow it to work in the real system. So on the right, you can see our pretty new results. We are developing new polymers that will be more compatible with NMCs, and the conductivities are still good at 40 degrees and even below. So now our challenge will be to integrate them in the full cell and also continue to improve the performances at very low temperatures. On the cathode side, we have worked both on the processing and on the cyclability of the material. So the first step was to prove that we were able to extrude the NMC material together with the polymer electrolyte. And to develop the catholyte formulation, because of course we didn't want to put PEO directly in contact with NMC. So we have developed the catholyte formulation and extruded it, and we got, let's say, promising results with a model electrolyte that was not PEO based. So the challenge after was to boost the performances of the cathode part, and this was done, as you can see on the slides. The first results were the red and dark blue ones, and we've tried to improve the performances, and now we get the pink and the light blue ones. So we already get very good cyclabilities at 40 degrees, and we still need to improve it at 20 degrees, but it's ongoing. We also have a big activity on modelization. Why do we do that? It's in order to, let's say, better understand what is happening both on processing and on the results we got. So we try to model the different interfaces to improve them. So we know that interfaces in the solid-state batteries are crucial for performances. It's not a breakthrough, but now we need to understand deeply what is happening in our system. So we are making modelization on lithium PEO interface. We also try to understand the compatibilities and the interactions between the different polymer we will put in the battery. How the PEO transfer its lithium to other polymers, to single-ion polymers that are integrated in the cathode side. And we also try to understand why the active material is more or less compatible with the different polymers. In theory, it's compatible, but in the process, we see that there is not a very good dispersion, why it is happening. And modelization helps us to understand and then go to the lab and try to find solutions. We have also, of course, activities in recycling. So in the recycling, let's say that there are two activities. The first one will be to recover lithium metal, and the second one will be to recover all the other components. So for lithium metal, we have the chance to beneficiate from Blue Solutions expertise who already have a process in their hand to recover the lithium metal. So we use this process, and after we work on, let's say, the remaining part, which is like a black mass and really looks like a lithium-ion battery. And currently we are developing all the recycling processes for recovering the polymer, the salts, and all the other components. So in terms of impacts, what we will deliver are two generations of cells, as I was saying at the beginning. The first generation will reach intermediate KPIs in terms of performances, around 900 watt-hour per liter. And the second generation will fulfill, let's say, all the requirements we want to reach in the project and reach 1,200 watt-hour per liter. So here you can see the, let's say, the details on how we are intending at doing that. So to move from 900 to 1,200, we need to work a lot on the lithium metal first. So we will reduce the thickness, but if we only reduce the thickness, you all know that it will never cycle for a long time. So we engineer this lithium metal, we improve the interfaces, we coat to make it working better. We also work a lot on the electrolyte. Why? Because we want to also decrease the price of the cell. And to decrease it, we try to incorporate the maximum of low-cost material, for example, PEO, which is very cheap, and reduce the, let's say, the expensive polymers. So from Gen 1 to Gen 2, we will only allocate expensive polymers to the positions where they are absolutely necessary. So in Gen 1, we put, for example, single-ion polymers everywhere in the cathode, but in Gen 2, we will only coat the active material with the single-ion polymers, for example. And of course, to do that, we need a lot of improvements everywhere to make everything compatible together. To monitor the results of this project, we are working with Renault to define very good KPIs and adapted KPIs to the application. So we have defined different ways to test the cells. So we will record different things, ranging from cyclability to power performances test, but also perform different safety tests also to verify that our cells are compatible and integrable in EVs. Our major difficulties have been to develop the electrolyte, and currently we also face some difficulties in prototyping because, as you know, NMC is very toxic, so we have lost some time before being able to extrude NMC because we needed to implement safety measures in the labs. So we are trying to recover this time and go to prototype just currently now. And then thank you for your attention.
Thank you very much, Mrs. Devaux. Mrs. Decuyer, sorry. Is there any question from the public? Then we can move on to the next presentation. Thank you very much. It's with project SEATBELT. It's Mr. Didier Devaux, who is scientist at the Centre National de la Recherche Scientifique. So please.
So, thank you for being here this afternoon. So, I'm Didier Devaux. I'm from CNRS. I work in a lab located in Grenoble. It's my pleasure to present you some results regarding the SEATBELT project. So, as the other project, SEATBELT, in fact, cover many different countries from Europe, with basically teams from academic industrial partners, as well as institute at the interface between academic and industrial scales. We are 15 partners, couple of affiliated, one non-affiliated, which is Imperial. And after 1 year of the project, we had the chance to include an additional partner through the Widera project call, so the open call, where we added a group from Slovakia that gave us the capability to explore more X-ray techniques to tackle the uncharacterized materials and interfaces. So we are around 8 million euros in terms of budget, and we are 2/3 of the project now. And in this graph, I just want to show you the work program. The Gantt is just to show you how we integrated the additional partners that basically is able to put his hand on all the different aspects of the battery development. And as with HELENA project, we are trying to develop a solid-state battery based on a hybrid electrolyte using as inorganic material halide compounds. And our strategy is to develop an in-situ-based material. I will show you later what it's about. But in terms of work program, basically we started somehow from scratch. As you know now from the presentation of the previous project, we need to tackle lithium metal make it as thin as possible to make it function, so to have a high Coulombic efficiency on the lithium side, and maybe have a coating in terms of interlayer, organic, inorganic. Be compatible with dry room and roll-to-roll process as well. And on the electrolyte side, we are trying to mix an organic, inorganic phase. I will show you some results right after this slide. And for cathode material, we choose lithium manganese iron phosphate, simply because it's cheap and of low cost. And all that go all together. We have partners doing also some atomistic modeling and machine learning to help to tune the microstructure of the electrodes and the electrolytes. And the goal is to have cell assembly, and as well in parallel, we have a strong activity in terms of recycling and safety analysis. And we decided, in parallel to the development of the different generation of material, to be able to know how the recycling capabilities from each material independently, and then we bring them all together little by little up to the battery cell. So SEATBELT is decomposed in different specific objectives. So we want to, our starting and driving route is the eco-design battery, and all those specific objectives falls in 4 different categories: other sustainability, materials, process, and safety. So these eco-design guidelines help us to know what kind of material is suitable or not suitable to be integrated in the battery system, taking into account recyclability, sustainability, and production in Europe as well. So we are moving to develop an in-situ hybrid electrolyte based on a biopolymer, and coupling that, we choose Halide electrolytes to make let's say, because it's a ductile material as presented in HELENA project. Why ductile is interesting property? Because it helps to reduce the pressure of the final pouch cells you will get at the end. So LMFP is our material of choice for cathode active material. Selected, we know it's not like NMC, but at least it gives good cyclability and decent energy density. And for lithium metal, this is the main challenging aspect of such projects, not only SEATBELT, but the other, to be as thin as possible and compatible with the material also in presence. And for production manufacturing, we choose also extrusion, which is a solvent-free process. And all that typically to be in line in terms of safety recyclability with the KPIs of the project. So in terms of dissemination, just a quick snapshot of SEATBELT. We have 1 patent and 2 more coming, couple of publications, obviously conference activities. I just want to point out 2 things. First, we are also sponsoring some conference on the way, scientific conference, and we are going to co-organize an international conference on polymer electrolytes next year as well. And also, in 2 weeks, we will have a workshop dedicated a winter school, if you want, on electrochemistry, where we will get about 100 attendees, postdoc, PhD students, and so on, all coming to Grenoble, so to disseminate the results of the project and give them also seminars on the next generation of battery systems. And why Grenoble is an interesting place? Because we have also access to 2 large-scale facilities, ILL, which is a neutron source, ESRF, which is an X-ray source. And SEATBELT also is collaborating through the Remade European project, and we got access to some different beamlines to be able to characterize our materials, and also, more interestingly, all the hidden interface in the battery device. As well, we are doing some clustering, let's say, activity with all the projects here in this table. So, in terms of results, I want to show you some snapshot of the different results. So what is driving us is the eco-design. The main takeaway message of these slides is to say we started from eco-design, which gives us guidelines in terms of material. Then we were able to develop, let's say, an ideal battery cells. So in terms of characteristic, thickness of all the different materials, loading of the cathode, etc., in order to reach the KPIs of the project, but as well go to the recycling part and thinking of safety, and then coming back to the cell development. So in terms of recycling, one of our main partners in the project is Blue Solution, so we are taking advantage of their recycling activity to be able to take out the lithium metal from, let's say, the battery. And we have also we are developing an entire process for each materials to be able to recycle as much as possible each different materials to reach 98% of recycled materials. And we are getting good results in terms of lithium metal recovery, as well as, so it's a combination of hydrometallurgy and as well direct recycling. And now we are now capable to direct recycle the electrolyte and to re-implement that in an electrochemical cells as well, with conductivity so far, and we hope to be close to the fresh materials. So the next step will be to see if we can integrate recycled material with fresh material and see how each of the material behave altogether. So I was talking about an in situ hybrid electrolyte. The concept of the project here, why in situ? Usually when you have hybrid, you are thinking self-standing film where you have a dispersion of inorganic in a polymer phase. Here what we are doing, we are taking let's say an organic phase, and we are just blending that with precursor of inorganic materials, and using the correct temperature setting, pressure setting, we can form the inorganic phase within the volume of the polymer to have a co-continuous phase. And this basically helps to reduce all the issues related to grain boundaries within the materials. And the process is compatible with dry room and as well as compatible with, let's say, technological development at our industrial partners. And now we are capable to scale up a little bit, these electrolytes. So the concept has been patented, and we are getting conductivity, let's say, very interesting and similar to a conventional ex situ mixing. So the bottleneck for all this next generation of solid-state battery is basically lithium metal. We want to make it functioning. So as PSIONIC project presenting, we benchmark a couple of interlayers, mainly inorganic, and also we have a partner, CRM in Belgium, who is developing by evaporation thin lithium metal, and we are comparing that at lab scale, notably, with thick, let's say, dense lithium metal. And this helps us to play with either the rugosity, the thickness of the lithium metal, or any porosity effect, etc. And using some electrochemical methodology, we are able to target, and we found out now that we are capable to process 10 micrometer thick lithium metal with correct cyclability. And what is interesting, our recent development, we reach one of the KPIs of the project, because at room temperature, we reach a cyclability capacity of 2 milliamp hours per square centimeter. Results then obtained at lab scales, and now the challenge is to go to a pilot scales and to confirm all these results. And for battery monitoring, as I told you, we have an additional partner who knows a lot about X-ray, and now we are assembling batteries at lab scales and monitoring the behavior of each materials and interfaces while the current is pulled through the battery. And we are doing also some imaging in order to guide us to select the correct formulation and material that at the end will go into the battery. The object we need at the end of the day is also a safe battery. Of course, you want to talk about materials, you want to talk about cost, but the consumer will be able to take and use this battery only if he knows that this is safe. And for that, we are developing kind of a new methodology related to safety, and we took advantage of in the consortium, we have CINEA and ILL, plus CNRS, and we developed, in fact, a kind of methodology using neutron imaging. Why neutron? Because neutron is very sensitive to lithium metal, so we can really image lithium metal during a thermal runaway experiment, and this is what has been done successfully dozens of times at ILL, and basically what we are provoking is to melt lithium metal and look also where are the failures and what lithium metal melting can induce in terms of failures to the subsequent materials. Is there onset of reaction, etc. So here, the so-called tour de force of this experiment is that with a very fast camera, we are able to capture the lithium metal and the degradation of the battery. So now that the methodology is set, we are going to disseminate the results in an open access scientific paper. We are now, in 2 months, going to benchmark the different configuration of the battery system related to the SEATBELT project. I had a video on the left. I don't know if it's going to work, but anyway, what is important is to show you that we can pinpoint at dozens of micrometer scales the location of the different issues in a time frame below 5 seconds. Overall, it's 5 seconds, but we are below milliseconds in terms of acquisition. So it's a lot of work in terms of data management and data treatment as well. Mid to long-term impact of the project. So we have a couple of expected impact. As I wanted to show you that we want to be able to recycle 98% of the battery and battery materials and to be able to reintegrate that in a new battery system that is under progress. It should be so affordable. I didn't mention that our LMFP is now being upscaled at the kilogram. So we are quite happy about that and going to integrate that so in the battery system. We are cycling so far at lab scales, and we are going to produce the first pouch cells in a couple of months now. The biopolymer, which is the organic phase of our electrolyte, is a biopolymer known to be recyclable and low cost, and this is also being upscaled right now by our partners in Spain. And the Halide electrolyte has been now selected to move on, and the overall hybrid electrolyte is being produced in a dry room at pilot scales now and being already direct recycled at lab scales. What is important also is to know that in terms of manufacturing, we choose a solvent-free process because it's not only safer for the user, but as well for the industrial worker later on in industry. And obviously, we are continuing and pushing to reach the KPIs of the project. So in terms of exploitation plan, we have a couple of generations of different materials that are now being taken by different partners of the project, and we are building our exploitation plan, and we'll see what we can get out of that. And more importantly, I would like to thank you for your attention.
Thank you very much, Mr. Deveau. Is there any question from the public for clarification? Then if not, thank you very much. And I would invite the next speaker. So for project ADVAGEN, it's Mr. Rahmandika Firdosa from Avesta, so solid state battery team leader at Avesta. Thank you very much.
Okay, good afternoon, ladies and gentlemen. My name is Rahmandika. Actually, I attend this conference together with my colleague here, with Aurelie from Toyota Motor Europe. Here we want to explain about the ADVAGEN project, which is development of advanced next generation solid state battery for electromobility. Yeah, the general overview of ADVAGEN project, yeah, more or less similar to previous project that already explained before, that this is a 48 months project from 2022 with 8 work packages, and we consist of 14 partners from 9 countries. And yeah, more or less the ADVAGEN consortium roles is divided to this scope. First one is the materials development, and then materials processing. Then we have prototyping and characterization and testing, then applications and modeling as well, and sustainability. It is as well for the LCA, and then with the recycling as well. And the last is the dissemination and communication and exploitation, which is needed for every project to try to be responsible to the public. And yeah, the idea for ADVAGEN project, we want to developed these 3 battery components. The first one is using a hybrid solid electrolyte, which is here if we follow the previous presentation about hybrid solid state electrolyte, mostly we have a different definition here, which is we have inorganic and also polymer and any other. But here our definition is to mix between solid sulfide and oxide solid electrolyte, which is we want to make this electrolyte to utilize the synergistic effect leading to higher ionic conductivity and stability. In this case, we take the high ionic conductivity from sulfide, and we utilize the mechanical stability for the oxide. And with the dense hybrid pellets can be obtained by processing at room temperature, which is this has been done in lab scale in the coin cell as well. And lithium metal anode, which is we try to develop the very thin lithium metal layers on copper foil by thermal evaporation, which we can control the thickness in by changing the several parameters like the speed of roll and then etc. And we use the protective layer with the investigator to provide interfacial stability against solid state electrolyte. For the information as well, for the lithium metal anode protective layer, we try to discuss closely with the international advisory board member as well, because we have inside our consortium, we consist of the academics, we consist of industry, institute, and many other part, but we also need the third part that we can get the insight, because somehow when we are here in the consortium, we are kind of biased. We want to make our project success, but somehow we forgot something that may be small detail there. And the last, we will try to develop the nickel-rich oxide as cathode as well. This nickel-rich cathode, we want to try to produce in Europe. So that's why we involve Serpotec from Norway and also IREC to evaluate the NMC 811 that produced. And this is the progress result. So far, the LPSCL conductivity that we got here, it's already more than our KPI for that. For all batches, which is produced by TU Brunswick here. And once we mix together with the LLCO, it has improved ionic conductivity for the hybrid solid-state battery system. And the next here, lithium coating process, we try sputter first with the ALOX coating optimization, that we can get several nanometers of aluminum oxide here, which is already proved by XPS as well. And we can validate in coin cell in room temperature here. We get around 130 milliampere hour per gram. And by the next objective, the trials for cathode layer manufacturing in the upscaling state, which is previously we try in the coin cell. Coin cell we got quite high capacity, but again for the cathode layer manufacturing, for the next capacity, which is more than monolayer, we have 1 ampere hour and 10 ampere hour, we need to optimize again. Because once we can use pellet or we can use the simple way to make solid state electrolyte in the coin cell, but for pouch cell or for 1 ampere hour to 10 ampere hour pouch cell, we cannot use the same method as well. So we have to tailor again based on the insight in the coin cell, then we can try to make, okay, the ratio is fixed, then we can mix with some other solvent and etc. Because here the tricky thing is sulfide is not that easy to mix with usual solvent, so we need to find the best solvent to mix as well. And this is the formulation that we use here. We try from 60% to higher, of course, and LPSCL and LLZO, you can find the ratio in our publication later, that in the range of 10 to 90, 20, 80, then we try as well for 30, 70. And the next thing in this objective is we got the design for the module designed by Ikerlan. Here, it's already applied to the European patent with the title of pressing device for a battery cell stack. This prototype, it's already bring to our general assembly, last general assembly, which is, prototype is still using the polymer. But in the future, there is some trials and also modeling there, which in this module, there is no spring or any other additional pressure that makes this module push the pouch cell. So we only hang on the materials which is in the side of the module, which is we can have some alternative here like the steel and as well for the titanium. So we will try to find the good model for that. And with the next objective here, again, like already mentioned by previous project as well, we need to know about the manufacturing or battery manufacturing from the technical in macro. Of course, we have to know what happened during the charge discharge or during the electrochemistry. So that's why here IREC have got approval for the synchrotron beam time in Albas Notos, and we settled the establishment for the collaboration with the ADVAGEN project. So there are several results already. Currently, we are preparing several publications for this, and somehow we try to achieve some kind of additional experiment as well. So that's why we cannot put here. Maybe later, if we invite again for the next RTR conference 2026, we can show. And the technique we use in this operando characterization is XRD, excess synchrotron, Raman, terse synchrotron, and ellipsometry. And the next objective, we try to see and try to align with the European regulation, especially for the battery regulation here that we all know that in this recycling, we need to recover the lithium, cobalt, nickel, copper, which is, it makes sense because if we can say now, mostly European battery industry still hang on the materials or raw materials come from, let's say, Asia. And then how to make Europe can not dependent anymore with the Asia, maybe later. Okay, now we still can give all of the battery come to Europe, but later we can try to, okay, we need to be dependent, we need to recycling, then we can use source from inside. And yeah, this is more or less the method that we can use, ultrasound assisted delamination principle, that the concept we try to put in the lab scale, it's already running. With the battery recycling pathway, we have several concepts here by using a thermomechanical pretreatment, pyrometallurgical pretreatment, and in the end, we will use a hydrometallurgical treatment to get the battery metal salts like cobalt, nickel, lithium salts. And yeah, the further recycling activities will start in the following months, then to prove the design submitted already in the deliverable. And yeah, I try to highlight here for the objective, the next objective, which is we need to have some strong collaboration with the battery industry, battery community. So that's why initiated by SPINMATE project actually, but here because SPINMATE and ADVAGEN coordinated by Avesta. So here I also try to manage with the Solid4B project. The first consists of maybe only 7. Start with SPINMATE, ADVAGEN, Amphorbat, Hidden, POSLion, and SEATBELT. Then several months ago, we start with PSIONIC as well. And then recently, we got collaborate with the SOLVE project. So the arrangement of the plan to market approach in ADVAGEN as well. We will try to collaborate with other Solid4B because in Solid4B cluster, we have like regular meeting, 3 to 4 months once. And by end of this month, we have another meeting which we want to have a workshop, particular workshop with these cluster partners about how to go with the IPR management and standardization, then this sharing in between all of this project. And yeah, this is mid to long-term expected impacts from scientific, technology, and industrial. This is more or less our path from January 2024. We have end of reporting period 1, and then we have 6 milestones achieved, 2 consortium meetings already done, and 10 deliverables submitted, with the end of 2 work packages, which is one of them is application and cell requirement, which is work package 2. That's why I bring Aurelie as well, because Aurelie is work package leader for work package 2. And we have 3 publications and 1 patent. Here, from TU Brunswick, Avesta and TechConcept, which is, this one is the collaboration between ADVAGEN and SPINmate. And third is University of Ljubljana, 1 patent from Ikerland, and actually 1 more, maybe soon to be patent, as the production of LPSCL. So LPSCL is produced by TU Brunswick. They want to patent not the LPSCL recipe itself, but how to make LPSCL. So they want to patent that method. And for economic, societal, and policy, first, ADVAGEN aims to produce cost-efficient batteries, which is actually, this number is already there in our previous project as well. And yeah, even though if we think now it's still maybe too far or something, still unreachable maybe, but at least we put an effort to how to reduce the cost as much as possible so we can reach this number soon. And societal impact, ADVAGEN has committed to open science assurance. So we have Zenodo account, we have some Cordis account as well to see how this project have a progress to implement and then to communicate, disseminate to community. And also we have some clustering activities. We have already 3 workshop and hybrid workshop to disseminate not only from ADVAGEN project, but all Solid4B partners. So in Solid4B cluster partners, we gather and then we try to invite on several speakers, several speakers, and then we try to disseminate on what the project achieved and what's the obstacle, what's the roadblocks of the project, so we can share together. So that's why in ADVAGEN, besides we try to discuss with the International Advisory Board member, we also try to use the Solid4B cluster as exchange information that, okay, our path is still maybe have a challenge, but all projects also similarly have the same pattern. So that's why we can say this clustering activity is important for every project in the future, because in the end, we can collaborate with the wider audience, with the wider battery community through this activity. And for the policy, of course, the ADVAGEN project with the cell design, recycling activities, and the life cycle sustainability assessment, as well other activities in ADVAGEN, we try to follow the latest European policy, which is, yeah, now we can say new battery regulation. This effort is expected could help to verify the policy, not only to follow, but we try to verify which is reliable, applicable, or have a high practicability. Yeah, as a summary here, ADVAGEN project have the challenging approach. Of course, every project have the challenging approach to match the R&D activities of the hybrid sulfide oxide solid-state electrolyte with the applicable implementation of lithium metal anode, NMC811, and with lithium metal, with solid-state electrolyte as well. So those extra effort will briefly tackled in this period, because we already passed the reporting period 1. In reporting period 2, later we'll try to demonstrate what we already achieved. Then later in the reporting period 3, we'll try to tackle as well. And yeah, the further series of R&D project, because we will believe with this 4 years project, maybe more or less the milestone, the path is already there, already settled from the lab scale, but until pilot line and then manufacturing in the industrial scale, we still need the time. So that's why we need to maybe yeah, this is our consortium hope. Maybe there is an ADVAGEN part 2, 3, or beyond ADVAGEN, I don't know. Will expectedly help to drive the output to the current ADVAGEN project. And yeah, more or less, thank you.
Thank you very much, Malika. Is there any question from the public? If not, then thank you very much. I propose we move on with the next. It's our last speaker, Mrs. Neha Malunaver from Austrian Institute of Technology will present the project AMFORBAT.
So this one, right? Thank you very much for your introduction. And I firstly thank BIPA and RTR organizers for giving me this opportunity to speak today and represent AMFORBAT project. I'm Sneha, I'm representing AIT. I'm a scientist at AIT, and today I'll be talking more about AMFORBAT project. As AMFORBAT project comes in the same family of solid-state lithium and battery technology as my colleagues already presented, but this bit differs from the conventional technology what you heard so far. AMFORBAT mostly focuses on additive manufacturing, which takes the technology for 3D printing, which is not the conventional way of synthesizing the materials. So before going to overall objective of the project, I would like to give you the brief overview of the projects. So this, as I mentioned earlier, this project concerns about synthesizing photopolymerizable electrolyte and photopolymerizable cathode, and also focuses on the development of anode material because it is an anode-less configurations. So there you can imagine, so this project brings together very diverse expertise of consortium together. And so far, most of the KPIs has been achieved in this project in terms of components development. And where I come from, AIT, we are mostly focused on the cell validation and testing of the components from coin cell level to prototype single layer cells and the multi-layer pouch cells. The consortium is formed of 10 partners, basically. Most of them are widespread in Europe, and we have 2 partners from UK who are mostly in synthesis of cathode materials, and the main coordinator of this AMFORBAT project is LATAT, who is situated in Spain. And the duration of this project is it started on 2022 July, and it will be ending in 2026 next year, same as the other projects in this family. So the broad objective of this project is this project develops the anode-free solid-state batteries by proposing the fabrication of VAT polymerization 3D printing technology for cathodes and photopolymerizable anodes to deliver 400 watt-hour per kilogram energy densities for more than 3,000 cycles with a retention of capacity for 80%. So to achieve this broad objective, the goal of this project has been narrowed down into smaller specific objectives, like first is to validate 3 ampere-hour pouch cells once the components has been developed, and the development of solvent-free photocurable polymer for all solid-state manufacturing of battery materials is undergoing. And the main KPI of this project is to achieve the high conductivity at room temperature, that is 10⁻³ Siemens per centimeter in terms of electrolyte, that too for photopolymerizable electrolyte. And the cathode materials which we propose in this project is aimed to achieve high energy density and power densities. And also we will be focusing on recycling and other social impacts of this project. So I'll be mostly talking today about the component developments in terms of electrolyte and the cathode and the development we have achieved so far in this project. To briefly give you the overview of the status of this AMFORBAT project, we are in the month of 32 already, and it consists of 9 different work packages. Work package 2 is mostly of specification of to specify the end user applications. Work package 3, 4, and 5 are mostly dedicated for the component development. Work package 3 is for solid electrolytes, 4 is cathode development, and 5 is current collector tailoring. And work package 4 is led by AIT, where we will be validating the cathode composite materials in the pouch cell and also in the cell level. Work package 6 is dedicated for modeling simulations, where we will go back and forth with experimental and comparison with the modeling. And 7 will come in the picture next year, where we will go already for the prototype and prototype 3 cell validations. 8 is work package 8 is like for sustainability impact assessments of this project, like what materials we are using. And work package 9 is dedicated for the dissemination of this project. So today I will be giving the brief overview of the development of 2 components, electrolyte and the cathode materials from this project. This project started with the how to go back? No, I think this is fine. No, this is fine, thank you. Sorry for that. So this project started with the development of electrolyte from work package 3. To start with the electrolyte development, we first started synthesizing the inorganic fillers for this photopolymerizable cathodes. So this inorganic fillers is used to first improve the conductivity in the polymer electrolyte and also used to improve the mechanical stability of the electrolytes. So this is a very important component in this material. And all the materials which were synthesized by the partners were screened with the commercial. So we know like the better understanding of these materials, if it can go to further step or no, otherwise we will just reject that material. And clearly the materials synthesized, LLZO particles synthesized in this particular project shows really high conductivity compared to even commercial LLZO, which is a good sign for us, and that too the conductivity has improved at room temperatures. So further taking this LLZO to next level, we actually incorporated it in the polymer matrix, which is very standard PU-LLZO. We needed this because to again characterize if these materials are worth understanding to go further for the photopolymerizable materials. And so, as my colleagues can agree that in solid-state electrolyte batteries, it is very important to form the percolation between the cathode and the electrolytes, because this is a very dry solid-state battery technology, and it is very challenging to form the interfacial stability between the cathode and the electrolyte materials. So we first cycled these cells with lithium, 2 different lithium plating and stripping to understand the stability of this particular electrolyte with the lithium metal. And we could achieve quite stable cycling, which you can see on your left side, where we could go up to 0.2 milliampere hour, which is really good for the solid-state battery technology current state of art. And we have a stable cycling around 0.02 milliampere hour. And also we tested in the commercial NMC BASF cathode materials, where the steps you can see is the different voltages we tested for this NMP to NMC, to see the voltage stability of this particular polymer electrolyte materials. And the final one, first we did the formation cyclings at very low current, C on 30, and then we went for C on 10. And here you can see all the materials reached to the cutoff voltage of 4.2, which is the voltage window of the NMC. And at around C on 10, all this, we had a very stable cycling for almost all the LLZO particles prepared. And interestingly, the LLZO particles prepared in the project shows really good performance compared to even commercial LLZO. Reference material. So we are still confident that these fillers can go for the further development of photopolymer electrolytes to achieve the end goal of this project. So this is the main focus of the project, where we are developing photopolymer by one of the partner Photocentric from UK. They are very well experienced in this kind of developing UV curable technologies. So here they have varied different solvents and polymers and photoinitiators with the starting material LLZO, and they have developed very thin material, and they could achieve the thickness for less than 150, which they're still working on to reduce still even more thickness to achieve really good compactability and also improve the energy density of this kind of particular materials. And the conductivity achieved so far for this main electrolyte is 10⁻³ at room temperatures. And again, this cell was tested with commercial NMC and lithium metal. As you can see, the performance is still promising, which is more than 120, which is really good performance for the state-of-art electrolyte materials. So the next step of this project focuses on the development of cathode and catholyte formulations, which is led by 3 different partners. And here the cathode material is developed in the project, which is not bought by the commercial ones. So to develop the most surface contact with the solid polymer electrolytes, all the cathode materials prepared in this particular projects were coated by different binders, and you can see the performance also. The uncoated material is lower compared to the coated materials. So this further coated NMC materials prepared in-house of the project will be going further for the photocurable catholyte formulations, which is led by Photocentric. So they are doing parallelly the testing of NMC with commercial NMC, if they can photocure or no, and then they have already tested with liquid electrolytes to make the validation, and further it will be tested on the solid state electrolytes. Here actually the partners are focused on optimizing different temperatures and the blade heights for the UV curable photopolymerizable cathode materials, and they have tested with rate capability at different C rates, and they could achieve really good capacity almost up to commercial, which can for the commercial electrodes even after the photocurable and addition of different materials. So it's going in a good direction, I would say, compared to like other NMC materials with other different kinds of solid state electrolytes. Given the challenges in this particular project, still it's going really good in terms of capacity and achieving most of the KPIs. So to briefly say about the mid to long-term expected impacts of the project, AmphoBat is trying to keep the promise it has made during the proposal writing. So the main focus was of 3D printing technologies, and the promise was given by AmphoBat to reduce the cost of the total batteries, and it has almost achieved to reduce 25 euros per kilowatt per hour. And also using low-cost photopolymers and photoinitiators. And the performance is expected to demonstrate the energy densities more than 400 watt-hour per kg, which we will be having more knowledge on this next year when we bring all the components together in the pouch cell level. And in safety-wise, we are happy that we are not using any fluorinated polymers, which is in a very high attention at this stage for which causes more environmental impact, and we are not using any flammable solvents. And the thermal stability in terms of final battery, we are aiming to reach for until 60 degrees to ensure the safe cyclability of the battery cycling. And in terms of sustainability, we are aiming to reduce the waste by 66% compared to conventional manufacturing and avoid toxic gas releases. And the stakeholders are predicting this technology can be used in line with the EV manufacturing industries. Yeah, thank you. So if you have any question, you can always reach out to me. If in case I cannot answer, I will always try to connect you with the concerned partners. Thank you.
So I would like to thank again all of our speakers for this very interesting solid state session. So my name is Guinevere Giffin, and I am the scientific head of the battery department at Fraunhofer ISC, and I'm very happy to be here to moderate the solid state session. I was one of the speakers here a number of years ago, and so it's very nice to see the progress that's being made compared to the very beginning, where actually SUBLIME was one of the sister projects of the project I was working in. I think today has been a good chance to showcase really the diversity of the research that's going on in the solid state area. We have 6 different projects, and we have 6 different solid state electrolyte formulations. And so maybe this would be, as an opening question before we move to all of your questions, which I'm very much looking forward to. With all of this diversity, how do we find a way forward? Is this really a chance in terms of market? Is there a market demand for all of these different chemistries, or is a hybrid possibly the way to go, and we need to bring the results coming out of all of these projects together to move towards a more singular solution? So I guess I would just like to hear your opinion, as with 6 projects with 6 different electrolytes, what you think needs to happen here. Who would like to start? So at the end from Amforbat.
Hello, can you hear me?
Yes.
Okay, so I'm new to this European Horizon project, so I can only speak for this one. Given my polymer backgrounds and what the technology is going forward with solid-state batteries, it is quite challenging. So in my opinion, I would try to focus on one component at a time, either electrolyte or a cathode materials, and first try to achieve long cyclability, and then focus on achieving the high energy densities and make the electrolyte work in a high voltage cathode materials.
Arash?
Yeah, for me, can you hear me? Yes. So I just want to make a reference to these semi-solid state cells that exist in the market, commercialized. So far, the only cell that we can see that is commercialized is this V-Lion cell, semi-solid state cell, 350 watt-hour per kilogram, and it is used in cars, and still they have difficulty to sell it because it's a bit more expensive than other cells. And they are not facing any of the challenges that we have in these projects. So they have only silicon, conventional separator, and they have only a little bit of electrolyte, for example, solid electrolyte in the cathode. So my overall impression is that so if something happens in the future, it might be much simpler than the projects we are focusing on. And I have not yet seen a cell with lithium metal anode that is commercialized. I mean, except for this with polymer, but I don't see it somehow. And here we all face challenges with the lithium metal anode in other projects, so it's a big challenge for us so far.
Yeah. If I can comment on your question, so it is true that we have now a very broad scenario with oxides, sulfides, and halides, as well as polymers as the main candidates. I wouldn't say that, okay, they are competitors, but what we are seeing now is that because they face different issues, some of them are shared, but what we start to see is that sometimes hybrid options are the key, or are a solution to increase or to improve the performance, or to address chemical reactivity. So we are seeing that LZO is very stable against lithium metal, so it can be combined with the sulfides. Also, sulfides have been recently used as interlayers with the halides. Halides can be very stable on the oxidation up to high oxidative voltage. So perhaps the solution may be from these hybrid concepts. Polymers as well, they offer very good advantages in terms of interfacial, improving the interfacial contact between these solid-solid particles. So probably there would be this hybrid approach.
Margot?
Mm-hmm. And now?
Now.
Yes. Maybe there are two things. The first will be the time to market. If there is only one solution that is industrialized at short term, I think that this one will take the lead, at least at short term. But if we take the hypothesis that we succeed for all of our projects and we succeed in industrializing everything, then I think that what will be important will be the performances at the end. And the customer, he doesn't care about what is going inside his battery, he doesn't know. So what will drive the market will be the performances, and the right performances with the right application, I think. So maybe some halides will go for certain applications, some polymers for others, and I mean the sulfides for even a third one. But at the end, this will drive the time to market and the performances. I think so.
Didier?
Is it working? Yeah. Thank you. To answer your question on my side, I strongly believe in synergies, as Margot and Pedro said. Basically, depending on the targeted applications, there may be a master player that need to be found, optimized, etc. So maybe one application will go to an oxide, sulfides, halides, or mixture. And as soon as this is identified, all the knowledge also gathered, developed through, like Horizon Europe project can perform and produce, disseminate, will be very useful then to focus and establish, to me, battery key technology that depend on the application. Could be mobility, electric vehicles, or high power application, for example. So we need this versatility to converge, to me.
Okay, thank you. So actually, to answer this question, based on one-on-one in our project, it's been a bias here, of course, because we're going with the project with this. Okay, I'm work with hybrid, and some other work with polymer, some other work with what. But the key point is, again, I want to highlight. I agree with the Margot as well, because in the end, the driver is the market, one, and then the second one is how we can try to use this output of this project. In the end, all of the project will get end, even though this have a successful 100% KPI, 80% KPI, or 50% KPI. But at least we have to think how to list this project. What's the key point of every project, and how this can be successful with this solid-state electrolyte. How this can be successful with this cathode. So in the end, of course, in this project, we look like competitors, but in the end, no, we are not competitors. We are together to build a better battery in the end, and then, okay, maybe I can steal solid-state electrolyte from PSIONIC, maybe I can steal the cathode from SEATBELT, or maybe AMFORBET, I don't know. Maybe in the end, we have to mix. So that's why, for the conclusion in my presentation, maybe the example is ADVAGEN. We need, okay, maybe we have the ADVAGEN 2, ADVAGEN part 3 or something like that. But maybe in the end, we can try to collaborate each other. That's the thing. Thank you.
Okay, so let's go to the audience. Are there questions? In the back. The very back row.
Yeah, hi, I'm Max from BMZ. So I think it was also a wonderful panel, wonderful talks. So first of all, thank you for this. I think it was a wonderful idea to compare these different materials in a sense. I'm thinking about, and this you also mentioned, one thing is what is the difference between these materials and what they have in common. And of course, have individual problems. For example, high pressure in LEP-SCl. PU has a problem with electron transfer to cathode, which we all know, or which we know about. But the problem I see in all this is the interface. What do we know about the interface? Before we have two interfaces, anode to electrolyte, electrolyte to cathode. Now we have maybe 5 interfaces because we coat the anode and the cathode. If we have hybrid electrolyte, we even have more. As you mentioned, we line semi-solid state batteries. To my understanding, they have a really deep knowledge about the interface, and this partially explains their success. So my question would be, what do you know about your interfaces of the materials, and where do you see the need or the problems there?
Who would like to start? Okay, Arash.
Yeah, so from my understanding, at least in SUBLIME, this was the case. For example, the interface we can engineer, for example, for the cathode to the solid electrolyte. So we can coat the cathode and it works with the solid electrolyte. With the lithium anode, we can also apply coating and it works with the solid electrolyte. But then when you make the processing, here is the missing information for the processing. When you make the electrodes and a lot of additional parameters kick in, and then what you have made before with the coatings, and you have protected your, for example, cathode and solid electrolyte and so on. And when you make the electrode, you have to re-engineer that again. And this is something I see in general Europe is lacking, because so far most of the cells produced in this research proposal were very, very small coin cells, and now when we want to go to real world 1 ampere hour, so we do this processing, and then a lot of knowledge is missing here.
Okay. About interface, I think that we don't know enough. The current approach is basically SEI, charge transfer. Everyone will speak about that, but basically we don't understand everything. When we don't understand, we put SEI. And I think that all these Horizon Europe project can help to better understand what is happening and figure out what are the differences between the technologies also. Maybe it's not the same thing with an inorganic interface and with an organic interface, but maybe it's the same thing. So I think that this Horizon Europe can be the place for better understanding. And for that, we have different approaches. We have modelization. In all the projects, we have modelization. And we also have access to, let's say, big equipments, deep understanding, deep acquisitions of the interfaces. And through that, I hope that Horizon Europe can bring better understanding. But if you look at the solutions, I think that we have all the same approaches, coating, trying to introduce a new material. But if we introduce a new material, we create a new interface. So I don't know if it's the best solution, but at the end, we all use this solution.
Didier?
Yeah, so just to answer you frankly, interface, we know nothing and we know everything about that. We know everything. We have access to modeling, large-scale facilities, multi-million equipment, so we can dig into battery system, look at all those interfaces during functionings, etc. And that gives a lot of knowledge, notably, to understand how material are functioning, interface, side products, etc. Now, and that would be, I would say, lab scales or some kind of small development. Now the story is, I know nothing, because if we move on to pilot scales or larger scales, will that knowledge locally can be implemented and, let's say, used to optimize a battery system at cell level at the end. And that, to me, is kind of retrofitting. Now it would be nice to have large cells, be able to go into that and see if we can correlate back our finding at lab scales.
Yeah, thank you. All the answer is quite good, and it's true. Actually, we know nothing about that one. But one similar pattern that we use now is how we can duplicate or replicate the solid state electrolyte as similar as possible with liquid state. See, now in liquid state we have only separator in the middle, which is mostly in the micron stage, like maybe 25 to 50 micron we can use with that. So how we can try to approach is how we make that lithium-ion pathway as thin as possible. Then we can try to use the artificial SEI as to make the interface. Yeah, we can say ion conductive pathway more better than usual trials. But again, if you ask about how about the interface, now we are still in the early stage, especially for the lithium metal anode, because for now I duplicate maybe previously already tell that there is no lithium metal anode commercial in the market for the robust understanding about that. So that's why it will be, yes, we know nothing, or we don't know nothing. Thank you.
I think we can all clearly agree that the key to having a good functioning solid state battery is going to be interface control. And it's really nice to see all of the different approaches that are going on here so that we're going to have solutions coming out of this. Are there more questions from the audience? Yes, over here on the left side. Or my left, your right.
Thank you for the wide panoramic view on this very important subject. And I'm maybe asking a kind of basic question out of pure ignorance. I see recurring numbers and targets. I guess most are coming from the call, but with variations in some cases. And one that strikes me is very recurring 3,000 cycles, which is extremely high for cars. I guess it's come from somewhere else, but for cars is extreme over design, particularly if you're going out up in density. Only one project that I could see splits with a target with cars, much more sensible, and another for planes. So the 3,000 is for planes, which makes sense. However, I don't see how this is defined. I mean, we had in the past problems because every project was defining life in their own way. So one question is there kind of agreed standard at partnership level or at cluster level, which if not, that would be a very important aspect. And if not, how does each project define it? Is it a realistic, so with you know, some constant, some acceleration, some fast charging, and things like that, or are we talking about standard, let's say, constant discharge for at cell level or whatever? In any case, I think that having a cluster like this would be a great opportunity to come to something like this for life, because this is a topic that I remember let's say the late Mario Conte already working 10, 15 years ago, and after that I haven't seen much, which by the way for the customers it's also an important aspect.
Who would like to start?
Maybe I can have some
Okay,
comments.
Pedro.
Thank you for this very important question. I will only focus on the realistic values that are being proposed here, and actually it has a lot of. It is very related to the previous question about these chemomechanical issues that solid-state battery faces. And what I can say is that for the moment we have achieved, we have reached. We have already materials with that fulfills the requirements in terms of performance, but the problem comes when we put them together. However, at lab scale, So in very small coin cell formats, it's relatively easy to make or to have good performances. We have, in the literature, you can find easily thousands of cycles with very promising performance. However, to understand how far we are from a real pre-industrial prototype, we need to know that upscaling from this very small scale to a pouch cell of just the size of a credit card is highly complex, and it's where it comes into role these issues with the pressure. So I would say that what we really should focus now on is on trying to get these performances that we have at small scale in these larger areas, which is very difficult because densifying the materials, which is a common requirement for all of the chemistries, it's very difficult in such large areas.
I think that those figures come from commercial vehicles, in fact, the 3000s. When you speak with OEMs more focused on EVs for everyone, the targets are closer to 1000. So the call aims at developing long-term batteries that will have less impacts on the environmental on the environment, but I think that those 3000s are not the focus for EVs. We have not developed that, but in the calls we also look at a second life for the batteries, and maybe in the 3000s there are 1000 for EVs and 2000 for other applications, but realistically you will never need 1000 or 3000 for basic EVs, because if you make 500 kilometers or 800 kilometers with one cycle at the end, it's not realistic at all.
I think the question you addressed is very important. In fact, all of those Horizon Europe projects, we have OEM on board, mostly from electric vehicle companies. In SEATBELT, we have Ampere, for example, or Blue Solution also. They all bring their knowledge and also, as you mentioned, their, let's say, cycling profiles and what kind of targets they need, etc., to reach market and application and so on. And we are driving by the requirement from the Horizon Europe calls anyway. But I think your remark is very important, and that's also something that can be addressed through the clustering of those projects, and I would be happy if we can have a dedicated session on that, because those clustering events are not there just to be beautiful and see how we can interact, etc. But we hosted one at our partner place, and at the end we had a very strong discussion, and it was challenging with different perspectives from different, let's say, specialists of different, let's say, environment. So that's something to address through clustering of Horizon Europe project, I think.
So, okay, yeah, go ahead.
Yeah, I think this is a very important point. I just want to mention that, yeah, because for example, for for cars, so we need only 500 cycles. If a car has a driving range of 400 kilometers, we need only 500 cycles to reach 200,000 kilometers. So this is like the average life of a car for many people. And then it means that 1,000 cycles is really enough for EV application. And I think at the end, for example, what we see that Chinese are trying to do is, for example, for LFP, the cycle life is normally like above 1,000, 2,000 cycles. However, I believe now they're sacrificing this cycle life in order to do fast charging. And for example, to add, I believe this is also coming that in the near future, they add some silicon to the graphite. This also reduces the cycle life. But at the end, the energy density, it increases, and still you have this 1,000 cycle that is perfect for EV application. So it is, I think we have to keep in mind to work toward this solution that is that makes sense for EV, for example. We need we don't need too many cycles. We have to just have enough cycles and enough energy density that works for us.
So, Pedro, you just made a point of we're working on the development of all of these materials. And then the question comes, how do we put them together? And so, if you think, this leads us towards the question of manufacturability. So the challenge going from small scale up to larger scale is how do I produce these things on, a pilot line and even bigger. So my question would be, what do you see in terms of manufacturability that's needed? What are the gaps to move towards a higher TRL? Particularly, what needs to be done in the field of manufacturing for solid state?
Yeah. For the challenge how to move on from the lab scale to pilot line and then to industrial scale. For now, as we all see here, most of our projects, we have a good result in the lab scale. Then again, we need to transfer or we need to translate that to the pouch cell, at least monolayer first, then 1 ampere hour, then 10 ampere hour, or maybe 30 ampere hour. This adaptation is not only from coin cell we can start with the pellets, but with pouch cell we cannot. So the real challenge is how we translate from lab scale performance to the pilot line manufacturing, then to achieve the same as lab scale, which is, this lab scale is the ideal thing. We can assembly inside glove box, which is in the manufacturing we have to try with the dry room maybe, with as standard as low dew point. Even we can use we can use fancy minus 60 degrees C, but it's not will be standardized because in the end the electricity will be high and everything. So the real challenge is how we can try to translate the manufacturing from the lab scale to the pilot line to the industrial scale. Then we need to meet together with the performance that it's already applied in the lab scale. So in the end, this question will have another question actually, but we have to learn together. Then what is the exact manufacturing we can approach? We can use polymer, we can coat directly on the cathode, or we can directly coat on a lithium maybe, or we can use mix first between sulfide oxide, then we mix together with polymer, then we coat, or we make freestanding. That will be the real challenge now.
I agree with that completely, so maybe I will amend my question. What is the key step, or what is the key challenge in manufacturing that needs to be overcome?
The first one will be the accessibility to the materials. We all start with few grams of materials when it's grams. And when you start an extruder, you need kgs, 10 kgs, 100 kgs. So the first step for Europe will be to be able to upscale all those fancy materials and upscale them with an accessibility in terms of money, because when you have a new polymer, often it's 60,000 euros the kilo. You will never buy 100 kilo, never. So this is the first challenge for Europe, to have people, industries that are able to upscale the material. And after, for manufacturing itself, I think that we have to think about new processes that will reduce the scraps, that will be adapted to these new materials. There are ways to duplicate the lithium-ion manufacturing methods, but are they the right and the best ones? I don't know. Maybe for certain applications like gel polymers, yes, but for inorganic, definitely not. So we have to think about new processes, ways to reduce the scraps, and being able to go fast. Because if we want to be competitive with lithium-ion, we'll need to process very quickly And to go quick, we need to process very, very, very quick. So everything has to be thought, and we need to spend time on all these details.
It's very nice to hear the answer. So how do we compare it to, let's say, existing lithium-ion construction? This was the same question that came 3 years ago, and now I think we're seeing that there are new developments in manufacturing from these projects, and this is a nice trend, and I think was one of the things we really have to continue to work on. Does anybody else want to comment on this question?
Yes. Maybe there are some battery manufacturers here that can provide more information, but what I know from these projects in which some manufacturers are involved, what I see is that the most challenging thing for them now is how to adapt the existing lithium-ion battery technologies to these materials, for which, for most of them, they require very strict dry environments. So this is a really big limitations, because if the materials are exposed to humidity, then they lose the complete the performance. So adapting the existing technology for this is, I believe it's really a big endeavor for them.
Yes, go ahead.
Yeah, just one comment to what my colleague said. I totally agree with them. But when we talk about processability, I think every researchers, not only in Europe, in worldwide, has to come in a midway where we design the processability for polymers, not just one polymer, just a class or family of the polymers which can be processed in a similar ways to reduce the cost of the manufacturing, which can be universal, where we can use everywhere.
So are there, yes, here in the middle.
Thank you. Yeah, my name is Daniel Buro, Volkswagen. First of all, thank you very much for the interesting insights. And I also like the fact that the discussion was going to the direction of automotive requirements already. It was mentioned that there's somehow a trend to sacrifice lifetime for quick charge. There is, however, also kind of a trend to sacrifice energy density for cost, because we are all very much cost-driven in the industry. So I think a very crucial part defining the future of solid-state chemistries is whether it will become a kind of niche technology for very high-performance applications like aviation or maybe premium sector automotive, or if there's a way to move the cost per kilowatt hour in a direction at the level comparable to conventional lithium-ion or even below. In one of the projects, it was mentioned that LMFP cathodes could be a way to maybe also bring costs down. I would be interested in your view on this comparative cost perspective.
I think that we will start with niche applications, as you mentioned. When the technology will start, it will not be competitive enough to go to very large market, I think. It will need some time to increase the volume, reduce all the costs, increase also the quality, the lean, everything, and this will bring a better possibility for solid state to go to lower cost. But even with that, if we want to be competitive, we need to select very deeply the materials, because the BOM at the end will be very important for the cost and the processes also. So the difference between low TRL and high TRL will also be how to understand how we can go to the simplest way to manufacture and the simplest way to assemble. How can we reduce the number of material we put inside? When we assemble a lab scale cell, we can put maybe 10 layers, we can put 100 materials, we don't care. But tomorrow in the industry, if we have 2 materials, then we cannot negotiate the price at the same level as if we have only one. So all of these small things will be important, but it will take time, and I don't think that we will be able to compete with lithium-ion from the beginning.
Yep. Yes. SEATBELT project, I mean, as the other project are, let's say, low TRL project. So obviously, to me, your question of sacrificing the energy density for the cost, for example, using LMFP or other materials that are cheap, makes sense, but also brings the question of social acceptance from the consumer. So we know that if you build an electric vehicle with, let's say, 200 kilometers range, it won't be, let's say, a hot-selling vehicle, I would say, and because you need to face also, if it's for electric vehicles, obviously, as you know, I guess, you need to have sufficient or propose sufficient, let's say, kilometers, let's say ideally 400, 500, just even if daily you do just only 30, 50 kilometers. So that's the first point. And to me, what is good with this project also, as we start somehow from scratch, is that we can already think in advance of manufacturing, processability, but also recycling. So we take into consideration, because we have many partners on board, somehow the entire battery value chain from the beginning, the need from everyone, from, let's say, from the consumer to the, let's say, OEM at the end. And that is also what's driving us, using LMFP, using biopolymers that can be cheap, etc., and recyclable in Europe as well, and sourced, also produced in Europe. And that, I think, is important. Black mass also will remain in Europe, ideally, etc., etc.
Yeah, thank you for the question. This question is exactly similar with the question from our International Advisory Board. During December, we have a meeting as well. So we try to break down here as how to define the cost. See, you mentioned about we play with the materials, we play with the cathode materials, changing maybe from, okay, we don't use NMC, we use LFP, we use LMFP, etc. But again, the cost parameters determined by first raw materials, and the second is manufacturing. So in raw material itself, like I already explained during the presentation, so far our raw materials, or at least precursor, we are still depending with Asia. So that's why in this all of project here, try to approach with recycling. Why? Because we want to approach in the near future. We can, okay, now we are hang too much, or we were dependent too much with the Asian source for the materials, but later, several years, maybe a couple of years or 5 years forward, all the batteries in Europe, if we can try to recycling and we can have already have a good raw materials, then we can have everything made in Europe. I think we can try to push the cost down. Any materials that we want to use. And then the second point is because we are working with the electrolyte as well. So the main concern is that electrolyte use the critical materials or not? So yeah, that's more or less about costs. Thank you.
So anybody who was here yesterday afternoon in the other, let's say, solid state system session, there was a big discussion about safety. And thinking back over the years, basically the discussion or the advantage of solid state has always been sold as, or at least one of them, safety. Solid state will be safer. So from the results on your project or what you're planning to do you think that solid state is going to be safer? I know it's a pretty direct question, but
I can quickly answer to this, that all solid state for sure is safer, but semi-solid state not necessarily. And comparing directly to the LFP, you cannot for sure say that semi-solid state is safer than LFP. This is my understanding up to now.
And maybe what do you think we have to do to get there? Yeah, keep going. Pedro, and then we can go down to the end.
Yeah, I just want to highlight that in principle, solid-state battery is safer from the thermodynamics, but I think we all have the duty here to really demonstrate it scientifically that this is true, which is sometimes we take this for granted, but we really need to make the experiments that we all have in the project, all this testing to really to say, okay, they are safer, but how much safer compared to? So this is actually, I think, a good, an important outcome that we will have from this project.
This comes back to the selection of materials and the selection of what kind of polymers. I think it's the responsibility of scientists who first initiates the polymers. There are electrolytes which can work in a wide range of temperatures. That's why we study initial thermal analysis for all the polymer kind of electrolytes. And one of my colleagues said, like semi-solid, he cannot promise it's safe or no, but I think that also again circles back to the what kind of additives you are using to make the semi-solid electrolytes. If we are going for organic solvents, it's hazardous for the environment. At the same time, it's not safe at high temperatures. But if you go for kind of ionic liquids, which are very well versed for high temperature batteries, I think it still makes sense. And we can say confidently that solid state can be operated at elevated, very high temperatures.
I think that we don't forget that we have lithium in most of this solid electrolyte. And the lithium is very reactive, and I think that once thermal runaway or another mechanism takes place, it can be really very dangerous. And another point is we have thermal abuse, but we have also electrical abuse and mechanical abuse. So we need to address all these different abuse to say, okay, it's more safe. Another point is we need to address also the impact of aging, the degradation of this material, and know more on this impact on the safety of the solid-state battery.
I completely agree with Sarah. It will highly depend on the content of lithium metal we will put in the cell. If we have a big excess, the stability of the cell will be very much degraded. And when the lithium melts, basically, you don't control anything. So the key point will be to ensure that we are stable till on 180 degrees. And the second point will be what happens when the melted lithium is in contact with our new materials. Which gas are released? What is happening? Does it explode? Does it just react safely? And this is what we need to assess. And I partially disagree on the semi-solid technologies, because if we choose the solvents with a high boiling point, then it can be competitive with other materials, within inorganic materials that are more reactive in certain conditions. So it really depends on the material we choose.
Just one point to add, like now actually researchers are moving towards the anode-free technology for solid-state batteries. So where we can get rid of lithium metal battery concern which we have. So this is one of the alternative technology for safer solid-state batteries.
Of course, this will also depend on the state of charge, where you have your safety question, but are there more questions? Yes, there, Bozok.
Thank you. So maybe, I don't know, I'm touching upon multiple questions that were asked today, and I hope it doesn't come out as a rhetorical question. But if you are somehow stuck at because of the high KPIs, especially at the performance level, I mean, safety, as you mentioned, is a different kind of a beast. But let's take the safety as a main kind of a driver for the solid state and compromise a little bit on the performance to really get to the next level. If the next level of a scaling in terms of increasing the size of the cell or the thickness or the coating, as Arash was mentioning, is so unknown for the next step, why don't we just, and to Ramonisko's point on the fact that the next step is just really, and we are going from we want to get to equal performance of the coin to the pouch. So why don't we just a little bit compromise on the performance, let's say energy density, and then we go to the next level and make sure that we have something to work on. I mean, it's just thinking out loud, maybe not that of a question. What's your take?
Thank you, Bozorg, for the question. Yeah, this thing is interesting that we have to wait with. Okay, we sacrifice some. I think maybe it is the similar question. We have to sacrifice the maybe energy density as minimum as possible. Not as minimum, as optimum as possible. Which is we can try to reduce a bit with energy density, but we don't sacrifice too much as well. But we can move on with something more niche, maybe the technology. Then we can move with the solid state electrolyte. But the thing here is not that easy, because in the end, if we stick to the performance, like okay, we put the minimum performance, then we move on, and then there is no innovation here. So this is the thing. The first thing, we find something, maybe tackle the problem in the community, in the society. But again, societies never ever have the enough. You know, society never get enough. Like now, okay, we want to achieve for the only EV technology, useful EV technology. But in the end, okay, how if we can reach for the luxury technology, how we can reach to the fast EV. Like now, we know the Formula E, we need as well for that. So that's why now maybe we already have the lease or maybe the technology that it's, okay, this is minimum, optimum we can use, then we move on. Okay, we can lease that first, but if we can optimize in the end more and more performance, why not? That's the thing. And then the second is, maybe this is connected with the previous question as well, because in the end, if even we are now here working with the solid state electrolyte project, but I believe we are not die-hard solid state electrolyte. You know, because in the end, we will find a way how to make market more promising. Then we can approach that kind of technology as well for better solid state electrolyte by, I already discussed with the moderator, it's fun. Is it really necessary for 100% solid state? Or we can try to approach quasi-solid state or semi-solid state, whatever the terminology we use. Because in the end, what society needs is this battery works with certain function. So that's why with minimum, it's okay. But if we can innovate more, it's better. That's from me.
Here, does somebody else want to comment?
Maybe very briefly.
Yeah, and then the question will be here on the side.
Yeah, what I find very positive of all these projects being on the same, having the same KPIs, is that at the end we played the same game, and with different chemistries, different approaches, and it will be very interesting at the end to understand which chemistry or methodology enables this performance, which one is better in terms of safety, in terms of cyclability, and all these KPIs will be all of them will be put together, and we will be able to understand better with all these outputs where we want to go.
The question here? The microphone, yeah.
Is more of a kind of a further comment, because I think the question before this one and so on are strongly linked, and with a session we had yesterday. The point is that the way I see your answer, you're looking at it at cell level. Now, of course, the more intrinsic safety you have, the better, but also that means temperature conditioning, a lot of other things. And then you have the system level. You might sacrifice something on one side at the cell level, provided that you know what is the pros and cons at the system level. So, of course, this injects another dimension to the problem. This is exactly why we had the call that we talked about yesterday about the system level design. Because, and unfortunately, there is, I mean, I would have welcomed that you were cooperating with them in order to do this kind of trade-off. While in the end there is one project, if I understand correctly, has an actual, let's say, solid-state battery, and the other are semi-solid and whatever. So we see part of it, as you said, but not all of it, or at least not, let's say, the whole space of the variables that we have. So I think that this kind of, maybe there should be a cluster of clusters between the guys working at the system level and the guy on the electrochemical side.
Any more questions from the audience? Or would anybody like to comment on this? Yeah, and then we'll...
Just a quick comment related to, okay, energy density, I mean, basically your question. Basically, we have also to look back at a little bit of history. If you look at the lithium-ion battery performance when it was released on the market by Sony in the 90s, basically, performance were very moderate. And then you have, what, decades of optimization, engineering, etc. But the basic concept remains the same. And to me, solid-state batteries, somehow, we know the basic concept, but this is just the beginning of the journey. And maybe one technology will take the lead on one market, etc. But as I said, the synergy and all the scientific, let's say, discoveries and the knowledge acquired will help to move on and hopefully to have a, let's say, progression lines that may be on a faster pace because to transpose from the lithium-ion, let's say, battery development. This is my feeling. I'm quite hopeful on that, in fact.
Thank you, Wout IJzermans, the Executive Director of the BEPA, the Private Sector Association, the Battery Partnership. And the cluster of clusters is, in the end, the partnership as well. So we are very happy to work with you, and we already have, and with the system level people to put you together and to work on building the bridges between them and integrating them. And even we see in the future calls that are under development, actually we're working in that direction because it is so linked, and especially if we go to a higher TRL, you need to work together and you need to have the end use parameters inside when you make the integration. So working on it is definitely is what we're doing. We're looking to learn from the projects that finish, the projects that are ongoing, projects that are just starting. It's an ongoing circle. So thank you all, at least from my side, for being here and sharing this. And we will continue with you on this journey going forward.
Yeah, Arash.
Can I ask a general question from a very high perspective? I would say from a very. So it's like in general, we see that, I mean, the share of NMC cells in the market is decreasing, and LFP is getting this share. And also for solid-state batteries, I've worked on solid-state batteries for almost 10 years now, and I am also evaluating the cells that are coming on the market. So for example, I've seen commercial cells, excellent performance. They are maybe 10% off from EV cells, but they are a bit more expensive and they are not successful at the end to sell. So I don't know, in general, this is a very open question that I have. So as a European Commission, what is your plan for next calls, for example? Because LFP, I see, for example, in Europe is completely somehow missed, so there is not enough invest on that, and now it's getting more and more share. And for solid-state batteries, what is your perspective? So do you want to push it towards all solid-state batteries? Do you want to push it to semi-solid-state batteries? Do you see as a shift in the strategy? So what is your perspective? Because you have an overview of all the EU projects that are taking place at the moment. And I would like to know also your opinion. So what is your feeling after following this project for several years?
I guess we're looking to the audience now to answer the question.
The problem is I'm no longer the European Commission, so I cannot, what I say has the benefit that can be changed at any time. The point is that that's my view. This is one of the few options we have to catch up. Because we are seeing that catching up with the current technology is unlikely, let's put it like that. And frankly speaking, which approach, I think is a bit early. I know that there are others coming. I was talking to a journalist friend that says that there will be a possible conference soon about that. And of course, if something arrives on the market, then we are, let's say, more in a hurry. But for sure, these kind of trade-offs that we were talking about, for instance, even if it's a bit more costly, but you have less, I don't know, thermal conditioning or whatever, they say, that's cell and then the system. So weight, performance, all this needs to be seen at this level. I don't know the ones you're talking about, whether you were talking about a system or cell level, so I might be wrong. But these kind of loops, it's important to get a kind of feeling of it when you do choices. I mean, I don't know, you have a certain component or a certain material that would solve you or would improve the safety, it would keep cost a little bit more. Okay, but at system level, would that allow a global reduction, for instance? And this is the kind of things that I was mentioning in my previous question. About the future calls, I think it's better that we ask.
So, a quick up, like most of people in the room maybe have already seen drafts of the 2025 work program. It will be published soon, I think. And if you look in there, there is a solid state or semi-solid state-ish, because the door is open there to just look at the KPIs and just not hang ourselves up too much on the solidness of it all. And also on your related question and the question that came from the audience on the design to cost chemistries, it's also something that's now being updated and addressed as it's seen that it's been. So we're also, it's a continuous learning curve, and also thank all the experts in the projects and also who use the partnership as a tool to actually influence the calls, because that's how we try to make better calls that are actually fit for the situation and the technologies that we have at hand. So keep your eyes peeled. It will be out soon.
I just forgot one thing, because you raised this issue of lithium pyrophosphate. I think we had the first project on lithium pyrophosphate called Helios, I think, something like 15 years ago. It had decent results, and it just said, no, too low density.
Yeah, I know this story. I mean, many companies sold their LFP plants, and also one of the big LFP producer was also sold to Indians, in Germany at least. So it's, yeah, this is unfortunate, I would say.
Questions from the audience? Well, we're slowly coming to the end of our session, and the next session, or the plenary session, is how to achieve circularity in the automotive industry. And so maybe as a way to sort of wrap up this session and tie to the next one, from my opinion, I think circularity in Europe is really a chance for Europe. And so I would like to pose the question to you. Sorry, I'm looking for my question here. You've all addressed recyclability in a way. And Didier, I think you said we need to address recyclability from the beginning. So what do we need to do for recycling in solid state? One, to achieve all of these targets set in the battery regulation. And two, to actually get the materials that are coming out of recycling back into the battery value chain, which at the moment is not necessarily the case. So what do you need to do as a project, and where do we need to look in the future? Who would like to start? Didier.
I think it's a very good and interesting question, the quality of the materials that you recover when they are aged, etc., in the battery system. So I think there is two things that are needed to answer fully your question. First is working, and second, knowledge. That's it. You need to work more and more and to understand. First, you need to be able to have battery cells, different format, cycle them, go to the end of life, be able to recover, acquire new knowledge, and so on, and reproduce. So I would say hard work will bring new knowledge, and also in this way we'll develop new processes, etc. And I think that's the important part, to really focus on how you process the materials, how they behave, and very importantly, have the somehow battery maker to accept to bring recycled material in their industrial lines. Because today, when you talk to industrial battery makers, they want, obviously, same quality of material with the same shape, etc. Everything is well aligned because it's their process. But if you bring recycled materials, you need also to address the variabilities, let's say, in all those materials. Could be shape, granulometry, could be coating, etc. And that also needs to be investigated and to give them and prove them that they can reuse and use recycled materials in their, let's say, industrial lines. That's my feeling.
Pedro?
Yeah, in my point of view, there is a lot of opportunities for Europe to innovate in recycling strategies because it is it's barely known for each of the chemistries we are working with. So there is a lot of opportunities for this sector to really provide solutions on how to recycle these electrolytes and the cell batteries.
Yes. First, okay. And then Margot.
Thank you. Yeah, I a little bit highlight for your question about maybe it's not necessary currently. Like currently it's still not necessary, right? Yeah, maybe it's not necessary, but it is a time bomb. Again, if we not try to optimize the recycling and not try to approach with, okay, this optimized approach maybe still not optimized in the future, because maybe in later insight will be improve. But again, even though it's still not optimized yet, but if we start now, I mean, if you can say the starting activity of recycling, it should be maybe 5 to 10 years ago, but the next is now. So that's why we try to optimize the method. We try to optimize the kind of branch on how we do, which is we have to disassemble first or directly shredding. I don't know, but because you highlight about maybe not necessary now, but it's time bomb. Because yeah, in the end, a lot of end-of-life battery will come.
Margot.
Yes, I come back also to the comment from Didier relative to the repeatability of the recycled material and the way we will be able to handle them in the industry. one point for recycled material will be also their purification and how we take them and make them as functional as the not recycled one. And the main difficulty for Europe will also be to bring back the knowledge on these aspects from Asia or other countries to Europe. Because, for example, if we take the lithium metal, we all buy it in Asia. And it's only in Asia where they know how to distillate the lithium. No one in Europe makes it. And we have also a lot of regulations in Europe that protect us, that protect people. And due to these regulations, it's also very difficult to implement that kind of industries in Europe. So we need to think about it in a wide way, taking into account our regulations, the lack of knowledge in certain areas, to be able to fulfill these requirements of recyclability and to be able to take the materials, purify and re-inject. Because if we only take the materials as they are, we will have issues. And as a researcher, we all look at the purity of the materials, how they are so perfect. If we take recycled materials, they will never be perfect, so we will never reach the performances we want to reach. So at the end, we need this knowledge, and we need this knowledge in Europe.
This question of purity always comes up with recycling. And I've heard the answer many times as well. We have to get back to the purity that we had. Do you think this is really necessary? Or is there a certain amount of impurities that we can accept to have a functioning circular product? Or is really, are these demands realistic?
It depends. It depends on the purity, on the impurities. Some impurities are not an issue. Some are really poisonous. So I think we can accept certain ones, but not the others.
Especially ones related to safety. Especially ones related to safety, I guess. That can provoke like plating or internal short circuit or something like that. So I think I'm totally agree with Didier. We need knowledge. So we need to have the cell or the material to recycle and to test it, and to be able to fulfill all the requirements. And yeah, this all put together enabling us to have more knowledge on recycling and the requirements of the application and safety, of course, in first.
This is really one of the nice things to see with the calls as they've progressed over the years, in that we are starting more and more to consider the aspect of circularity and to consider end of life from the beginning. And so in the future, then the next, or sort of the follow-up to that would be, how else can we design, other than recycling, design circularity into our cells? Do you think that there are aspects that could be brought into solid state that doesn't have a huge penalty? Or is this something that is still kind of completely open that we have to look into in the future? Sorry, I didn't mean to stump you on the last question. I know this is certainly a challenge, simply because there's always the compromise. So back to Bozorg's question, the compromise of performance versus getting to the higher TRL, the compromise in terms of lifetime, in terms of cost, in terms of all of these things. And I guess the question is going to be, what are the compromises we're willing to make? Is circularity a compromise that we want to make? I think it's one we need to make to a certain extent, because we need to have an eye on the materials, and we need to get them back in the value chain. So I guess as sort of a tie to the next one, and what I would at least be interested to see what comes, is how can we really achieve this aspect of circularity, and what do we need to do? on that note, I would say we're pretty much out of time. Did you want to?
Yes, so thank you very much again to the presenters. So maybe as a general conclusion, so I understand that indeed the optimization is an ongoing and a never-ending process. There are a lot of compromises that can be made, as we discussed as well. And I think we should keep in mind probably the two transversal areas like digitalization, which you mentioned also in some cases, and recyclability and improving sustainability, which remain an important topic as well. So, yeah, thank you very much, and wish you all a nice rest of the conference.
So the next session is the plenary session back in the auditorium, and it starts at 5:30. So you can have a few more minutes for the coffee break before the next session, and thank you all very much for coming.